Hello, everyone, and welcome to Clopen Mic Night. This is our fifth Clopen Mic Night, and the eagle-eyed among you might have spotted that today's date is also relevant. So today's date is the 1st of the 5th, 25, which is 5 to the power of 0, 5 to the power of 1, 5 squared. So we have suitably called this the power of fives, and we have four excellent acts and a host, me, making five. And I am your host. So my name is Sophie McLean. I am a PhD mathematician and a maths communicator, and I will be your host for this evening or whatever time it is where you are. Because although it is 8 p.m. in London where I am, and presumably 8 p.m. in the rest of the UK, we do have some viewers from around the globe. So welcome everyone. And actually, if you want to put in the chat where you're from, we'll try and do some shout outs throughout. Now, before we get started, a few things just to mention. First of all, this is a maths variety night aimed loosely at adults, which means there might include some swearing and occasional rude words. Now, if you're happy with this, and you're happy for any younger offspring or children or pets in the room to hear these words, absolutely fine. But just be aware, it is 8 p.m. where we're filming, therefore, we're kind of past watershed. Now, also, saying this because although we're not expecting any particularly complicated themes, this is live. So what happens, happens. So we will see. And we will look forward to seeing what happens and enjoying the nature of live broadcasting. So with this, we also have on our YouTube chat for everyone watching live, the ability for you to get in touch with us. So some of our performers will be asking you guys questions, but also if you have any thoughts, anything you want to shout out, then please do let us know. With that though, although we know that you're going to get really passionate about the maths, we do have a code of conduct just to make sure that everything stays nice and friendly and the fun maths community we're all used to. The code of conduct is in the YouTube chat, YouTube description, but for anyone that hasn't read that or doesn't want to scroll up, I can let you know. So the key things are: don't engage in exclusionary behavior or language, harassment, bullying, aggression, or elitism, or make exclusionary jokes. Not even ironically, because you might know you're joking, but whoever's reading it might not. However, puns, absolutely welcome. Inclusionary jokes, yes, please. Jokes where you explain the meaning, even better, because everyone knows a joke gets better and better the more you explain it. We're also going to be using gender neutral language where appropriate, and respecting people's pronouns as an inclusive space. And really, we're all here to do maths. So that's the main thing. If you do have any concerns with anything, we have Clopen Mic team members moderating the chat, but also we have an email address, hello@clopenmicnight.com, where you can email any concerns, but touch wood, that shouldn't be necessary. So I've said the word Clopen Mic Night a few times by now, and you might be wondering, what is a Clopen Mic Night, Sophie? Well, Clopen is a mathematical term generally used to refer to sets that are both closed and open, because in maths we can do that. And some of the best words in maths are just spliced together. I think my favourite is cline, which is a curve and a line. And the reason this is both closed and open is this is an open mic night in the sense of everyone performing today has just stuck their hand up and said, hey, I want to perform. But it's closed in that you as a YouTube viewer cannot join now. There will be an opportunity if you want to also stick your hand up and say, hey, you can do that for a future event. But we have curated our lineup of talented speakers, performers, and fun maths nerdy people for you today for this show. So for that sense, it's closed. Also, like an open mic night, some of this is going to be the first time these people have been performing these sets and routines, just like you might get in an open night scratch night. Imagine we're all in some really cool comedy club and then make it cooler because that's the kind of people we are. So it does mean that things might be more rough and ready, but that's where it gets exciting and fun. And that's why it's even more fun if you send all your love in a chat. We do have a mailing list, clopenmicnight.com. You can find out where to sign up to the mailing list. We also have the general socials, Mathstodon. We have Blue Sky. We are still going to tweet things out. For the people in our audience that still use Twitter and find it hard to move over to other things, we got you. But we have the other things available for anyone that has left Twitter behind. So now on to the show. We have four acts who I will introduce to you, who will each be performing for about 8 minutes each. Now, if you love these acts, which we're sure you will, there are two things you can do. You can put in the chat how much you love them, but you can also donate money because this is free. But if you want to support the acts and support some of the behind the scenes team and things, you can donate to our coffee, which if Scrogs, one of our ever beloved, underthanked behind the scenes people, is paying attention, he will put up a link, hopefully somewhere here. So thanks for that, Scrogs. So I think it is time for us to get cracking. I have been speaking to you for about 7 minutes, and I think you are not here to see me. You are here to see our wonderful acts. So our first act is Mats Vermeeren. Mats is a research fellow and lecturer based at Loughborough University. And he kind of sits at the intersection between maths and physics, as do many of us. Although I myself am a pure mathematician, I do occupy a physical body, so I can relate a bit to that one. And he loves talking about maths. Again, very relatable. And today, Mats is talking to us a bit about what will happen if you zoom in and zoom out. Now, I'm going to leave it at that. But welcome, Mats, and take it away.
Hi, Sophie. Yeah, thank you very much for the introduction. So to be a bit more precise, the question I want to ask today is a bit absurd, and I'm not sure Loughborough University and the APSRC were expecting to see their logos next to a question like this when they decided to support my maths communication work, but it is what they're getting. So I'm asking, what if suddenly everything in the universe started shrinking? Now, if you have some thoughts about this, feel free to put them in chat. I think we'll probably have to fine-tune a little bit what we mean with this question. And since the universe is a big place, I suggest we start slightly smaller. What if everything on Earth, including the Earth itself, suddenly starts shrinking? So the planet and each object on it start shrinking, and then it's probably not this that we want to see happen. So what I've done here is that each object shrinks to its own center, and then suddenly our astronomer and the local Loughborough landmarks are floating in space. No one's going to enjoy that very much. It's also a little problematic because if I say each object shrinks to its center, then I need to define what an object is. What I've done here is shrink the astronomer together with our telescope as one object, but I could have taken them as separate objects and shrunk them separately. So this is kind of ill-defined. And it gets even worse if you ask the question, is an atom an object? Because if an atom is an object and each object shrinks independently, then we start with this lovely crystal lattice, and all the atoms start shrinking, and after a little while, the bonds are broken, and all we're left with is dust. And, well, there's not much interesting physics you can do if everything is microscopic dust. So if we want to solve this, to me, the most obvious way to change things is that not just the objects are shrinking, but also the bonds holding them together. So what we need to do is we need to change the size of everything in the universe, but also, in a sense, the size of the fundamental forces, the length scales at which the forces work. If we change them so that they also get smaller, then our bonds can shrink together with the atoms, and our whole crystal that we see here just gets smaller. And if we scale that back up to the whole planet, it will also be slightly less distressing for its inhabitants. Then everything now can shrink together and well, not have any obvious change. And if there's not any obvious change, then as a scientific mind, we should ask, well, is there any change? Is there any measurable change? So let's imagine that our scientist on the world here suspects that maybe there is shrinking going on, and they decide to measure this. So what could they do? They could take a giant ruler and measure the Earth. Okay, it's easy. The diameter of the Earth here is about 2.8 giant rulers. And then everything starts shrinking. But everything in the universe, that includes the ruler we are using. So if they measure again now, the diameter of the Earth is still 2.8 rulers. So the measurement at the end will give the same result. And you may think, well, a physical ruler, a giant ruler, is not a great way in practice to measure the size of the Earth. Maybe you want to use the speed of light and measure how long it takes a signal to get from one side to the other. But if we're in the setting that we agreed, or that I forced on you, where all the fundamental forces also change and the constant of nature change to accommodate this shrinking, then the speed of light, for example, would also slow down. So no matter what physical property you use in this context to measure the size of the Earth, you will get the same measurement before and after. So through the eyes of the inhabitants of this world, absolutely nothing has happened. Now that's a bit of a boring conclusion, but it's not a conclusion because the question I asked in the beginning is not what if the Earth started shrinking, but what if the whole universe started shrinking. Now, you could expect kind of the same thing to happen, although when you think of a crystal lattice and atomic structure, it's very tightly bound together. When you think about the objects on Earth, they're pulled quite tightly by gravity. And the same for the solar system, say, there's still a very strong interaction. But if you imagine two very distant galaxies in the universe, the empty space between them will be so big and so the distance so large that the gravitational interaction between them might be effectively zero, completely negligible. And if we take that point of view, then we're kind of back to the first situation where each object shrinks to its own center. So each of these galaxies shrink because they have forces in them holding together, and we're shrinking those forces as well. But since their interaction is negligible, they each shrink in their own place. Now, could the observers in this world measure this? Probably yes, because what's happening to their ruler is still the same as before. Their ruler gets shorter. So if at the start here, they measure the distance between the galaxies to be about 4 rulers, then later on, they measure again, and the distance between the galaxies is now maybe 8 or 10 rulers. So we can visualize their perspective maybe a little bit better if we play exactly the same animation, but at the same time zoom in on our astronomers to get their perspective. So from that point of view, what they observe is something like this. So in this very absurd thought experiments where everything is shrinking, what they observe is that all the galaxies are moving away from each other. So they come to the absurd conclusion that their universe is expanding. Now, of course, we know this isn't an absurd conclusion. The universe is expanding. That's been observed over and over again. And maybe you still think that this thought experiment is a bit of a silly coincidence. But if you actually look at the mathematical models used in cosmology, they do not describe a universe that is growing into a larger space or something like that. In the models, the fabric of the universe stays the same, but what changes is how we measure within the universe. And that's true in a lot of cosmology and in a lot of mathematical geometry as well. The geometry does not come from the shape of an object, how it sits in a larger space. All the geometry comes from how you measure within the geometry. So the universe is expanding. Yes, that's good physics, but the mathematics behind this is that all our rulers are actually shrinking. Right. Now, Sophie, how's chat doing?
Hello. Yes. So chat is enjoying the talk. We've got some good puns going on. Um, shall we open the chat to see if anyone has any questions?
Yeah, by all means.
So, okay, if anyone wants any questions, you're welcome to put them in the chat now. Um, I love this about the ruler shrinking. I do have a question though. When you said we're going to ignore gravity, like if I ignore gravity, I'd be on the ceiling. Isn't that cheating?
I mean, yes and no. So in that situation, gravity will be very weak, but something that's weak is not always negligible.
Hmm.
It's a bit arbitrary. They said, well, within the galaxy, gravity holds everything together, but between galaxies, it does not.
Hmm.
But there's actually a very good reason in this story to say that gravity is different from the other forces, because gravity is also an effect of what the rulers are doing. And
Okay.
so it's again an effect of it's not something happening with the universe, it's something happening with how we measure. So if we shrink rulers everywhere, um,
Hmm.
then we get the expanding universe. But if you think about gravity, you may have heard this has something to do with curvature of space-time. And mathematically, curvature means that different places have different rulers. So what happens for gravity is if we put a heavy star here, for example, it will shrink the rulers near that star. And that's mathematically exactly what curvature is. You have different rulers in different places, and that will change the paths that are your shortest paths. So it will change how everything moves inside the universe, which is how you get gravity, at least according to Einstein. So
That
it's
is so
a
cool.
little bit cheating, but it was cheating with a purpose.
Cheating with a purpose is the best kind of cheating. And please don't take that quote out of context. We do have a question in the chat from Nick Vermeeren, who I assume you might know. Uh,
Never heard of him.
no relation, just a pure coincidence. The surname's the
Pure
same.
coincidence.
Um, if the real universe is shrinking and hence we feel like it's expanding, would we be able to measure it? And if so, how? And is this already being done?
The problem with this is that all the measurements are completely equivalent. Whether you say that the universe is expanding and everything in it is staying the same, or the universe is staying the same and everything in it is shrinking, I can think of no possible way of measuring the difference. And there's a very good reason why we usually say the universe is expanding rather than everything is shrinking. Because most of the time when we're doing physics, we're not talking about the whole universe. We're considering small things like the Earth or the Milky Way. They're very small compared to the universe. So if you're only looking at a part of the universe, it makes a lot more sense to say everything in there has a fixed size, all the laws of nature are fixed, but the universe is expanding. That's much more convenient to work with than to say, well, the universe is fixed, but everything's shrinking and the laws of nature are changing.
And are much less damaging to our egos to not say that we're shrinking.
Exactly.
I guess we have time for one more quick question. Saoirse says, really interestingly, what happens if we shrink and then go back to the original size? Will there be a measurable change?
Well, that's kind of one of the possible scenarios for the life of the universe. One of the scenarios would be you start from the Big Bang, everything expands up to a certain point, and then it starts contracting again, and you get a big crunch. In this perspective, that would be you start with infinitely long rulers, they're shrinking, and then they reach their minimal length, and then they get very long again. So we measure the universe to shrink again. So yeah, it is possible. I don't think it's quite settled what the future of the universe holds in store for us.
Oh, amazing. Well, I guess we'll look forward to hearing more research. Maybe in the next Power of Five when it's five for the four coming up. Then and then we can find out the answer.
Yeah, I think you
Um,
get an experimental physicist on an astrophysicist instead of a mathematician then.
okay, well, thank you so much, Matt. Before you go, is there anything you want to say or anything you want to plug? Have you got a website we can look at?
I've got a website, just matsvermeeren.xyz, so my name.xyz. I'm on Mastodon, although I'm more of a reader than a writer on there. But yes, and you'll find my contact details quite easily online if you ever want to get in touch. So yeah, thank you very much.
Oh, well, once again, thank you very much, Matt. And let's have like a round of applause, the age of the universe or the size.
Right,
Thank you.
thank you very much.
So it is now time for our second speaker of the night. And this is, I am very excited for this speaker. So Yolanda Ahini works in medical imaging and is a researcher in Manchester working on this. She is an awesome and lovely person to boot. So kind of ticks all the great boxes of the kind of person you want on Clopen Mic Night. And actually, I've heard rumors about this talk that it might involve a wooden recorder. So let's see where that goes. Welcome, Yolanda. Take it away.
Oh, thanks so much, Sophie, and thanks for the invitation to speak tonight. Yeah, my name's Yolanda Ohini, and I'm a neuroimaging scientist. And so, neuro is, of course, the brain, and imaging is imaging inside the brain. And so, my research focuses on developing new imaging techniques to probe deep down into the brain to try to better understand diseases like Alzheimer's disease. Now, I'm a physicist by training, and I feel like the work that I do in imaging is actually quite hard to describe. But I thought that actually, seeing as this is a maths night, it might give me the opportunity to try to use some unusual techniques to describe how MRI works. So, MRI is magnetic resonance imaging. And if I just show you an image of an MRI here. And some of you perhaps who are watching may have had an MRI before. And so this was a real revolution for healthcare because we're able to probe deep down into the soft tissues inside the body. Now, MRI consists of a few different things. You need a very strong magnet. And so the strength of an MRI magnet is about 1.5 Tesla or 3 Tesla. And so if you go to a junkyard if you find a magnet that's able to pick up a car, that will probably be at around 1 Tesla. So these are very, very strong magnets. And what you also need is a magnetic gradient and a radio frequency pulse. Now, a radio frequency pulse is at the end of the electromagnetic spectrum, which has a very long wavelength, and it has a frequency of about tuning into BBC Radio 4. And so what happens in MRI scans is we ping some of the radio frequency pulse into the body. Now, because our bodies consists of a lot of water, about 70% water, these water molecules are actually at the same resonant frequency as the radio frequency that we ping into the body. And so when we ping it in, the water molecules will jiggle around, and when we turn off this radio frequency, it will sing back to us that same frequency. So I've just brought my recorder, you might see that here, to demonstrate this and to demonstrate actually how we're able to get an image. So if I just stop sharing for a second. So we ping the radio frequency pulse into the body, and then our water molecules sing back at perhaps this frequency. Oh, that was a bit feeble, actually. I think I could do a bit better than that. So I'll ping some radio frequency pulse into the body, and our water molecules will sing back at this particular frequency.
So, Yolanda, interestingly, Zoom loves frequencies and loves filtering out frequencies that don't sound like voices.
Oh,
So,
no. So no sound at all. Let me try one more time.
this is a very
Did you pick?
beautiful miming of a.
Oh, well, that is a shame. But well, it's a good job that I actually prepared what I was going to say on the next slide. So unfortunately, no recorder. So I'll have to you'll all have to just think about my recorder skills, and I'll just have to show you with the diagrams. So basically, I was singing back at a particular frequency. Now, all of the water will have that same frequency, but we want to determine where each particular water molecule is in space so that we're able to form an image. And so in order to do this, we have to put a magnetic gradient to change the frequency across the different water molecules within space. So if I just start sharing again. So I was going to describe this on the recorder, but unfortunately Zoom is not my friend today. So I'll have to show you my images. And basically what I wanted to tell you is that during my PhD, to kind of like understand my body a bit more, I actually tried to see how many images of different body parts that I could get. So basically the first image that I was able to get is, of course, of my brain, seeing as I'm a neuroimaging scientist. And this is what my brain looks like. So this is inside my head. And basically, if we were to think about what the different frequencies at the different locations would be, at one end, we would apply the magnetic gradients, and then at one end it would have a low frequency, and as we move across the image, this frequency would increase. Now, it's not only the frequency that we're interested in, it's also like the signature of what's within that particular environment. So as well as the frequency, which will change at the different locations, depending if there's lots of grey matter or a combination of grey matter and white matter, or maybe even cerebral spinal fluid, which is a fluid within the brain, these will all have slightly different signatures. And so this would give us a different signature across the brain. And what's really cool is that we collect all of that signal with a frequency detector, and we use a mathematical tool called a Fourier transform in order to untangle all of those different frequencies and to be able to give us those different contrasts of the different molecules across the brain. So unfortunately, my recorder didn't work, but perhaps you got a little insight into actually how using the different frequencies, we might actually be able to get the different image contrast across the brain. Now, after going to have my brain scan, I have a friend who actually works in cardiac imaging or heart imaging. And so I said, oh, can I come and get to see what my heart looks like? And so he was like, okay, I'll see if we can fit you in some developmental scans that he was doing. And I know that we always see this, the biology picture of the 4 different ventricles of the heart. But when in real time, this is what my beating heart looks like, which I thought is quite incredible that we're able to actually, as well as capturing that static image of the brain, we're able to collect these dynamic images of inside the different moving parts within our body. And what's really cool about my friend's work, Dr. Tom Roberts, is that he is able to actually track the movement of the water molecules and work out in which direction they're moving to be able to get the flow of the blood moving through the heart. So some of you might have seen, a vector which looks something like this, and you'll have the vector will be pointing in a few different directions, probably 3 different directions. And overall, you can see actually what's the magnitude, and the principal component of that vector will tell you in which direction most of the blood is moving. So this green arrow, it would be our principal direction vector. And so he's actually able to map out all of these little components within the heart, and to be able to get an image something like this. And so this is able to show us the movement of the blood through the ventricles and down the aorta, which I thought was amazing. And I think this is really the beauty of when maths some physics meets biology and what we're able to do using these different tools. So this the different arrows will give us a direction of the blood flow. And then finally, I have another friend who actually specializes in gut imaging. And so I think the gut is one of the places which still baffles a lot of medics to understand different conditions such as irritable bowel syndrome. And so the work that my other friend was doing was to look at imaging the gut. And so in order to be part of this study, she said, don't eat anything. And then when I got to the hospital, they said, oh, we want you to drink this drink to kind of get your gut going. So I said, okay, no worries. And they said, we'll come back in half an hour and see how you're getting on. And they said, you'll probably need to go to the toilet. And I was like, okay, you're really going to get my gut going here. And then the doctor came back and said, okay, we're ready to take your gut scan. And I thought, oh no, I haven't been to the toilet yet. And he said, okay, the scan is going to be 20 minutes because the movement within your gut, this peristaltic motion, which also, like your heart beating at a particular rate, your gut is also whirring at a particular rate. And this is much slower and it's over about 20 minutes. And so I had my gut imaged and I was sitting in the MRI scanner and I thought, wow, that is the longest 20 minutes that I've spent waiting for this image to be taken. But luckily, I survived and I was able to get the MRI of my gut. So let me show you the gut image here. I hope you can see that okay. And it's a bit of a weird image, so let me just orientate you around this picture. So up here is the liver at the top there, and then there's the back, so I was lying on my back, and then here is the large intestine. And so like the cardiac image showing the blood flow through the ventricles, this MRI image was also a cine image, so it's capturing the motion of the gut. Now, I know that we don't have 20 minutes here to wait for the full image, so this is actually sped up, so it's not in real time. But if I play this video here, we should be able to see the gut moving a little bit. And then at some moment, we should be able to see that peristaltic motion of the gut as all the stuff is pushed through. Oh, and there it goes. It's such a bizarre image, and it's funny to think that this is happening all of the time, every 20 minutes within our bodies. So I suppose all that's left for me to say is sorry that you didn't hear the recorder, but also I suppose sometimes thinking about my research and imaging the inside, it's not what's on the outside, it's perhaps what's on the inside that counts. So thanks a lot for listening. My name's Yolanda O'Keaney, and yes, thanks for having me.
Thanks, Yolanda. I mean, what I'm getting from this is you have a lot of friends and all your friends are cool. Thank you for coming to talk to us. Before you go, do you have anything you want to plug? Anything you want to share there?
Well, at the moment, I'm doing lots of research, but hopefully after the summer, you might catch me at New Scientist Live. So if anyone's going to London, then I'll be around there, and perhaps some things before that, but TBC. So focusing on research until after the summer.
Oh, it sounds like some exciting things in the future, and very looking forward to New Scientist Live. Hopefully many of us will end up there and we can see you, which would be awesome. So thank you, Yolanda. And yes, I hope you all imagine Yolanda's excellent recorder playing. So we're soon going to go on to our third speaker. Can't believe we're halfway through already. Just before we do, I want to mention and remind you about the coffee. So if you've enjoyed watching Yolanda, if you've enjoyed watching Matt's, then do please let them know by even just giving a £1. And I'm just looking in the chat as well. There's a lot of love, a lot of claps going on. So thank you all for that. But I think it is time for our next speaker. So, you've all heard of the terms big data and AI and very large language model or large language models and things. They're all kind of quite zeitgeisty at the moment. But the next speakers thought, okay, you've heard of large language models, but what if we were to take that idea and just make it worse? What if we had a very small language model? So, please welcome Christopher James.
Thank you very much, Sophie. While I'm talking about small language models, I'm actually going to start with a music model. When I was working on this, I found it, hide that out of the way, useful to think about a small example. And the smallest example I could think of was Twinkle, Twinkle, Little Star, which, in case you don't know, sounds like this. Hopefully this comes through. Can someone let me know if it doesn't? And if you didn't know Desmos could do that, you do now.
And also, we're learning a lot about Zoom's Fourier transform and how it filters out noises because some of that came through. So by the end, what with Yolanda, this, and our final act, we'll be able to pinpoint exactly what Zoom does and doesn't like.
If there's a setting I can change, if someone can let me know, I will change it.
There.
Otherwise, I can carry on and we'll.
So you could actually change it by changing your sound to original audio for musicians on Zoom, but it might take a bit more guddling. So we'll carry on and then potentially a reprise if we have time at the end.
All right. The way I generated that is with an Excel spreadsheet. I have Twinkle Twinkle Little Star. I have its notes here. I have a VLOOKUP doing this, and I have the start and end for each note. It's a really bad MIDI file. And the first thing I can do with that is just jumble the notes up. It's a really bad approximation, but if I press this button, the screen hopefully will change. And you'll see the colors switch. It is being very slow. My computer does not like running all of those things. There it goes. And this is exactly the same notes, but shuffled up. It's going to be a terrible version of Twinkle Twinkle Little Star. And rather than doing lots of copying and pasting, here is one I prepared earlier. So it's all of the same notes, but in a different order, with the same rhythm. I'll talk about some of my editorial choices later. That sounds exactly the same. Right. Nope, that didn't do what I wanted. 1 second. Just copy this. Drop it in there and try again. And I think it doesn't sound unlike Twinkle Twinkle Little Star, but it doesn't sound particularly like it either. And one of the reasons for that is we're ignoring how the notes in the piece link to one another. So I have a little graph here, a Sankey diagram, and within that you can see, so C is the first note of it. C will either link to itself half the time or to the note G half the time. And we've got these different transitions here. And we're not taking that into account when we look at what is going on with this. And I've got an annoying Zoom thing in the way. Don't know how to move that. Ah, it's gone. So what I've done is taken that and I've set up this thing in Excel. So the next note is not independent of the one that was before it. So for example, here, it's picking the first note G at random. And you can see that color-coded over here in orange. And in the piece, Twinkle, Twinkle, Little Star, G is followed by the note A twice, the note F 4 times, and the note G 4 times. And what it's doing is this is counting up how many times those notes appear in total. And then over here, this formula is just pick a random number between 1 and 10 and tell me what that note is. So it picked a G at random, and then a G again, and then a G again. However, on the third time round, it then picked an A, and then the A over here, it stayed as an A, stayed as an A, stayed as an A, then it went back to a G. And so what this is doing is it's picking out, it is a big conditional probability tree, really. It's picking out different notes, but every single pair of notes is one that already existed in Twinkle, Twinkle, Little Star. And if I put that into Excel, then it sounds a little bit like this. Which is not the same, but it does have more of the features. It has that descending feature. And that's because if we go back to this diagram, the letter F, the note F, always goes to itself or it goes down. And then the letter E either goes to itself or goes down. And so there's always, when you hit an F, there's always this descending pattern. And we've managed to recreate that. I then became a bit ambitious and looked at a much bigger piece. It's another fairly well-known piece. It's by J.S. Bach. You might recognize it if this comes through. I won't play you the whole thing. Sorry, I'll stop that. I won't play you the whole thing. It has about 550 notes in. Oh, thank you, Sophie, for telling me it's coming through. It's more complicated. It has more notes. I've spread out. It covers about 3 octaves in total. And the transitions between it look like this. They're quite messy. However, there are still some patterns in there. And what I have made it do is the same thing. And I am conscious of time, so I'm going to skip a little bit. I've done the same thing here, where I can balance it where one note follows the previous one, but I've taken this one a step further, where in fact here, every triple of notes exists somewhere in the piece. I've simplified what it looks like a little bit because Excel was struggling. But the key thing here is if I click on a formula there, you can see it's looking at these 2 notes, so the G and then the B, and then it's looking at these 2 notes and it's comparing them, and it will give me a 1 in this box here if and only if this note is a G, then this note is a B. And that happens somewhere down here, further to the right, and it says, let's just reset itself, which is fine. I'll just take a moment to catch up. So every single pair in this, every single triple in this is a triple that appears in the real piece. And if I play that, again, here's one I prepared earlier, it sounds a little bit like the real piece. But not very like it. And you can see there's a lot of noise. If you just compare the pictures, this is the original one. There's lots of structure in there. And this one, it's just a bit more random about. I played this to a colleague earlier in the week, and he said it sounds a bit like 1980s video game music. Sorry, this is the 3 one. But there's a little bit more structure. Now, I took it one step further. And I've done this, so it looks at sets of 4 notes in a row. So here, it's looking at these 3 notes and it's comparing them. And if the first 2 notes match, then it will look at the next note and it will generate it from that. And so every single set of 4 notes in a row here match up with something in the real piece. And that hopefully sounds like this. And if you know the original piece, you'll recognize little fragments within there. And the lesson here is when you have more data beforehand, it predicts more accurately what's going to come next. That's not an original thought. Claude Shannon in 1948 wrote this exact thing. It's a really important paper, and he's doing it with letters. And he has this idea that you can just pick letters at random. It won't be very good. And then here, he's just picking letters at random with the correct frequencies. That's what he calls a first order approximation. I have done that exact same thing in Excel, and it looks like this. And Sophie gave a warning about potential rude words earlier. These are randomly generated letters. Sometimes there are 4 in a row that spell things out. Sometimes it's a rude word. I'm sorry if that happens. I'll explain how this works. It's a little bit different from the AI one, from the music one, sorry, that I made. But I press this button. This is the 1 bit of code. It's an Excel VBA that's just refreshing the spreadsheet. It is not actually doing anything. And there it is, it's refreshed. So this is picking every letter independently from each other, but with the matching frequencies in the English language. And you can see here and there are word-like things. So for example, we have the word moan over here. We have the word, maybe appropriately, poet over there. And there's a few others in there, but it's not very good. In order to improve it, we can do the same thing that we did with Twinkle, Twinkle, Little Star, which is look at the pairs of letters. Now, this is a bit complicated to set up. What I've done is I found some data. It was quite hard to find data about the frequency of letter pairs in English. And I've just said, if I had, I think it's about 20 million pairs of letters, how many of them would be double A? How many of them would be AB? And then this is just looking at it cumulatively, and it's picking up here a random number and going down that list and picking it out. So everything is picked proportionally. And if we run this one, where now every single, I don't know why it's decided it doesn't like that, every single pair of letters is picked proportionally to its frequency within the English language. So the next letter is not independent of the one before. Oh dear, this has all gone a little bit wrong. We get slightly longer words some of the time. So we've got, ooh, what do we have? There's almost experience there, soul over here, firm is a common part of a word as well, and it's a little bit better. I couldn't find any good data on trigrams of 3 letters in a row, and I can't code, so I couldn't just download something and search for it. What I did instead was do something that is a bit more complicated, but it's also predicted by Shannon in his paper. I took The Cat in the Hat, which is out of copyright and has been for a long time, but happily for us has a lot of repeated words. And I'm doing exactly the same thing as I did with the music. Every pair of words here, the second word restricts what the third word can be, the third word restricts what the fourth word can be, and so on. And it's generating a random arrangement of the words in The Cat in the Hat, and the new version of The Cat in the Hat goes like this. A cup on her way home, do to have no make them go away. I do, said with big bumps, jumps, and the strings. It's not great, but if we do the same thing that we did earlier and change it to triples, again, I can have this randomly generate them, but now the 2 words in a row must be followed by a third word that exists with the 3 words in that order within the book, and suddenly it makes a lot more sense. The fan and the strings and the cup and the milk, and the fish, and he gave them a pat. They are tame, oh so tame. They have come here to play. He should not be here when your mother is not. It's actually grammatical. It makes sense because this is a very simple book. It has 1,600 thereabouts different words, words in total in there, and actually a much smaller number of different words. There's a lot of repetition, and you can genuinely get some sense out of this. But the most ambitious one I did was I took the complete sonnets of William Shakespeare and I made this write new sonnets. I did it for pairs, they're not great. I did it for triples, they're okay. And then I did it for sets of 4 words in a row. So when I press this button, it will regenerate and we will have along the top of the screen a new Shakespeare sonnet. Time for the canker, vice the sweetest buds doth love. What thou presentest, a pure unstained prime, thou hast passed by the ambush of young days, either not assailed or victor being charged. Again, it sort of makes sense. It sounds vaguely Shakespearean. And the reason for that is we've run into a problem with our data. There are some words in here, the word zealous, for example, only appears once. So if we end up at the word zealous, the next word is completely predicted. And what I found is that any good phrase that appears has already been written by Shakespeare. And there is a bit of randomness in there, but essentially what I'm doing is plagiarizing Shakespeare. I'm very sorry. But for me, this is what AI sort of is. It's not very good. It takes a lot of effort, and it's just copying other people. But at the same time, you can do some quite fun things with it. Thank you.
Thank you, Chris. That was great. Wow. Looks like if you want something like ChatGPT, but with less of an environmental impact and keeping the plagiarism and misinformation the same, it would appear, then we've got our solution. We do have to quickly move on to our next But before you go, how can people find you?
I believe there's a link somewhere on the website, and I will write this up at some point if people want to play with it themselves.
Excellent. So keep your eyes peeled on Chris's socials if you want to work out how to play with this yourself, or have a go. See if we can create some competing ones. We've had some great people in the chat picking out their favorite words at the beginning. So thank you very much, Chris. It's been great to speak to you. And now swiftly on to our final act of the night. So how do I explain our final act? Our final act is the pseudo-random ensemble, PE for short. So it's going to be a PE that we all can enjoy for once. Try and create some great memories of PE. And the members of the pseudo-random ensemble, in, of course, a pseudo-random order, are Martin Harris, Sam Hartburn, Lucy Rycroft-Smith, Colin Beveridge, and Gavin Phantom, who are all appearing on screen now. Now, there are many facts about the pseudo-random ensemble, but we have an unrandom, very specific, not much more time for this intro, so I will leave them to it. Please welcome the pseudo-random ensemble.
Thank you so much, Sophie. Right, moving very quickly on, we have a totally normal song for you. There are 2 ways that you can join in with our song. We will have the lyrics to the chorus on screen, and there should also be a PDF coming up in the chat. They're very simple lyrics. You can join in, sing as loud as you like. I want to be able to hear you. The second way that you can join in is to we invite you to write your own verse. You'll get the hang of it really quickly. Write a verse, pop it in the chat. If we have time at the end, which it sounds like we might not, we will sing as many as we can. Here we go with our totally normal song. I know a kind of normal that will never disappoint. It's a vector that's orthogonal to a surface at a point. If you modify its measure to make it unit-sized, you'll find your normal vector has now been normalized. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal, and all of them are weird. Does anyone else know a kind of normal?
I know a kind of normal.
Take it away, Colin.
I have a kind of normal I'd like to reveal. The set of normal numbers contains almost every real. Write out all the digits, pick a random string. It's just as likely to have been any other thing. Pi and E and gamma, the 7th root of 4. We think they're likely normal, but I couldn't say for sure. Not convinced it matters, it's nothing to be feared. The only thing we proved is that it's normal to be weird. Many kinds of normal, more than I can say. Try to learn them all, it'll take 100 days. Word has been exploited, over-engineered. There are many kinds of normal, and all of them are weird. Does anybody else know a kind of normal?
I know a kind of normal.
Hit it, Gavin.
By smoothing normals, you can make a metric curve. The polygons are finite, yet slick lighting is observed. But when you choose which way to cross, there is no room for doubt. If you get the sign wrong, then your surface will be inside out. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal, and all of them are weird. Oi! Does anyone else know a kind of normal?
I know a kind of normal.
Hit it, Martin.
Thank you. I know a kind of normal, how things are distributed. The center is quite prominent, the tails are more muted. These lines vary in length. The first two were quite standard, and the third one was much shorter, and this last one keeps on going. From strength, 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 strength. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal, and all of them are weird. Oi! Does anybody else have a kind of normal?
I do.
Over to you, Lucy.
Thank you.
I know a kind of normal, horizontal to the vertical. It's so very important that it gets the definite article. English joke there. You might remember drawing it from mathematical curricula. You just find a line to start with and go perpendicular. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal and all of them are weird. I know a kind of normal, not really mathematical, the opposite of eccentric. In those aristocratical. Sadly, if you don't have wealth, you'll get a different word. Behind your back, they'll call you freak, and to your face a nerd. But let's be serious for a moment. Non-conforming is a bold and courageous statement, and we should all be proud to make it. I'm here for the people they call the weirdos, the freaks, the geeks, the goblins and the gremlins, those who just don't understand why Love Island is so popular. You're not alone. There's nothing inherently important or good about being the center of the distribution, the middle of the curve. The moral of this tale is, if you're in the tail, it's okay. If you're out near 2, 3, or even n standard deviations, it's okay. Be that deviant in the deviation, the outie, the outlier in the outfield of normality, because normal is a social construct designed to constrain our behavior. So we buy things, swallow things, perpetuate myths, consume, conform, and comply. It doesn't even exist. As we learned from the Air Force cockpit design story and Quetelet's quantitative analysis, it's damaging, it's mathematically inaccurate, and I say, resist the normal, be the glorious exception. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal, and all of them are weird. Does anyone else know a kind of normal?
I have some more to say about normal.
Oh, let's hear it.
To find more kinds of normal, I looked on Wikipedia. I thought that it would help, but it only made me needier. So many definitions that I never ever knew. And what the little critters mean, I haven't got a clue. There are many kinds of normal, more than I can say. If you try to learn them all, it'll take 100 days. The word has been exploited and over-engineered. There are many kinds of normal, and all of them are weird. All of them are weird. Oi!
Oi.
Woo! Applaud myself there. I hope you enjoyed our song. Sophie, have we had any more lyrics in the chat, and have we got time to sing them even if we did?
We have 0 minutes to sing them, and everyone has been so enraptured by this song and the message that we actually haven't got any yet. But should we say if anyone does, they can record them, take videos, and then maybe tag you guys in them?
That would be amazing. I would love that.
Okay, so the pseudo-random ensemble details, you have all the standard socials, I guess.
We do. We
Also,
have a website.
you have a website with merch, I hear.
There is merch.
So
Ta-da!
if you want a pseudo-random ensemble t-shirt like Sam is currently sporting, then you can go to the pseudo-random ensemble website. So thank all 5 of you, and please keep being weird. Now,
We're there. Thank you.
and that is a wonderful note to end our show on tonight. I want to say thank you all for coming and watching, whether you're watching live and have been engaging and chatting with us in the chat, or indeed whether you're watching this on catch up and are going to see it later, or are watching it for the second or third time. as I believe many of you are doing it. Now, just a few things for me to say before we wrap up. We have a feedback form because what maths communication thing doesn't have a way of evaluating how it went, which we would love it if you could fill in. But also, if you haven't joined our mailing list, please do. If you haven't followed us on Mastodon, Blue Sky, anything but To Our Houses, then please also do that. And once again, thank you for anyone who has donated in coffee. It has been wonderful to have you all here. Finally, keep an eye out for the next one. This is Clopen Mic 5. There will be a Clopen Mic 6 in some pseudo-random amount of time once again. But thank you all so much for coming, and we hope to see you next time. I've been Sophie McLean. Goodbye.